The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So we're going to be talking about normal modes. And you've already done a normal mode calculation on cis-acetylene, so you know most of this stuff. But the notes contain a lot of stuff worked out completely on water, which is simpler than the case you did, but it's also, there's more here than what you did. And we will deal with the vibrational normal modes of water and then make some comments about why are certain internal coordinates mixed and others not. And that brings up the concept of symmetry, making symmetrized normal modes, which block diagonalizes both F and G matrices. And then a more general or discussion. Once you have symmetrized, you might have a mixture. You might have states of the same symmetry species, a bend and a stretch, and what makes them mix or not. And so some discussion of how do you read these matrices and infer causality for mixing of different kinds of internal motions. So read F and G matrices. And there'll be some discussion of kinetic energy coupling and potential energy coupling. And then a refuge for the ill-prepared, I go to something that I know very well, polyad. So if we get through all of the notes, we'll end with a description of the coupling among many systematically near degenerate levels, and that's the menu. Okay, so we have a whole bunch of transformations. We start out with Cartesian displacements. We do mass-weighted Cartesians. Then we go to internal coordinates. And then we get to the normal coordinates. And we have some equations like this. This relates the internal displacements to the normal displacements. This looks like quantum mechanics, but it's just a form of a shorthand. And it says, okay, the jth normal displacement is given by the rules of matrix multiplication. So we would have a sum over I of L minus 1 I J S J, except that I did it wrong. No, I did it. Well, S sub I J I. That's good. Okay. This is the rules for, who's beeping? Outside. Okay. All right. So this is the rules for matrix multiplication. And this is telling us that if we had this L inverse matrix, what would we do? Well, we would take the jth row of the L inverse matrix, and that would give us the information that we need to construct the jth normal mode from all of the internal displacements. And I'm always troubled or confused about, do we want the row or the column? Do we want the inverse matrix or the non-inverse matrix? And there's only one correct answer, and this is it. Okay. We describe the internal displacements using these ST alpha matrices, displacement vectors. Alpha refers to the atom T refers to a particular internal displacement. And these things are vectors of length 1 pointing in the direction where a displacement of 1 causes the maximum increase in the specified internal coordinate. And a normal mode would involve harmonic motion of all of the atoms at the same frequency. And okay, so that's the review, which the stuff you know. And now let's talk about water. So we have a structure of water. We'll call this 1, this 2, this is, and 3. This is conventional. You would think 1, 2, 3, but this is the way it's most often labeled. We have an angle, and we have 2 bond lengths. Okay, and what we want to do is describe all of the internal displacement coordinates and build up the F and G matrices with which we can solve for all of the problems. So by we know that there are 3n minus 6, or 3 normal modes. There'll be 3 linearly independent internal displacements. These 3 are a linearly independent set. We can call one of them, and there's no reason to worry about the numbering of the internal displacements, but there is a reason to worry about the numbering of the normal modes. And so we can choose whatever, or we can call this, we can call the stretch of the 3-1 bond S1, the stretch of the 3-2 bond S2, and the bend S3, and we then do the problem. Okay, so in order to express these internal displacements, which are motions of 2 or 3 atoms, subject to the constraints that we don't want to move the molecule and we don't want to cause rotation, we go through some vector analysis and we get the expressions for the little st alphas for the 3 atoms and the 3 internal displacements. And that's a beautiful bit of vector analysis, which I will not do. And it's in the notes. And the important thing is that you take this example and you apply it to a problem which is not too complicated, and you get this, you get the same results. So I mean, ideally you'd apply it to water or D2O and see if you get, if all the analysis is correct. Now, one of the things about these guys is there are no masses involved. And that's always bothered me, because you would think that you'd describe the internal displacements in a way where you don't move the center of mass. But that's not it. You're moving the 2 atoms, equal and opposite amounts, in a bond stretch.
The S coordinates for a mass weight.
That's wonderful. Yes, they are. So that takes care of that completely. Fantastic. I didn't understand that. Thank you. I mean, it's always bothered me. Every time I go through this, I see no masses. And they're already in there. Okay. See? We all learn here. Okay, so we derive these little S vectors, and we can build up each of the internal displacements subject to the constraints. Now, one of the things you find is that here we have 2 stretches, and these have units of length, and here we have a bend which has a unit of angle, and these don't have the same dimensionality. And if you don't like that, you can define a different bend internal displacement simply by weighting the change in angle by the equilibrium bond lengths of the two bonds, and then all of the internal displacements have the same dimensionality. This actually makes you feel better because the matrices we're going to develop, the F and G matrices, they also have elements that have different dimensionality. And so that goes away if you make all the internal displacements have the same dimensionality. However, even though these matrices have elements with different units or different dimensionality, when you expand the matrix to get the, to evaluate, when you expand the determinant, that's supposed to be a number. And in that expansion of the determinant, you're multiplying a whole bunch of numbers. And every term in that sum of products has the same dimensionality, whether you do this or not. But it's a good way of checking to see whether you've made a mistake. If some element in one of the matrices has the wrong dimensionality. Okay, so we can do this or we cannot do that, as you wish. Okay, so first step was figuring out these little ST alphas, because we want to draw pictures of the displacements. The next step is to compute what's called the G matrix. And this is a matrix that contains masses and geometry. And it's used to evaluate the contribution of the kinetic energy to the total Hamiltonian. Now, there are a limited, this is so beautiful. I get a little thrill every time I look at this. When we're worried about the vibrations of polyatomic molecules, when we talk about internal displacements, they involve a very small number of atoms. 2 for a stretch, 3 for a bend, 4 for a torsion. And you can have much, much bigger molecules than that. Yet, there is a limited number of topological cases. And if you're clever with vector analysis, you can work out all of them. And some of them are pretty evil. The torsions are terrible, especially torsions combined with other things. But it can be done, and it has been done. And so the papers by Decius and the book by Wilson, Decius, and Cross, it's all done there. And so then you don't want to have to do this. You want to be able to look up all of the relevant elements of this G matrix expressed in terms of the things you know. And because it's a little bit complicated in general, the elements of this G matrix are tabulated in a kind of code. It's a very elegant code. But it's easy to make mistakes in interpreting those elements. So there are more than 4 types of elements of the G matrix. The simplest one is something that's denoted like this. RR just means 2 stretches. Now, the elements are not tabulated with R and R prime. It just means it's a stretch interaction. It could be diagonal, it could be off diagonal. And 2 means 2 atoms. That means it's the element involving the same 2 atoms twice. And there is a diagram that goes with this symbol. And this just says, okay, we have atom 1 and atom 2, and 2 circles around atom 1, 2 circles around atom 2 means that this is a matrix element between 2 internal displacements. The same 2 atoms are involved in both, involved here and here. Now we could, if we had something where we had 3 atoms and 2 circles around 1, that would be an interaction between one stretch here and one stretch here. That would still be RR, but it would have a 1 up there. And so it could be straight, it could be bent, and these things tend to have numbers on them because the elements that are tabulated make use of those numbers. And so it's a good thing to exploit the numbers. We could have 3 atoms connected, circles like that. And you know immediately that the only way 3 atoms could be involved in both motions would be for a diagonal bend-bend interaction. And that would correspond to 3 atoms and phi, phi. And again, they should be numbered 3. Now, I don't know why the numbering is topologically different for this, and it's possible that I screwed up on one of them. And we could have a bend-stretch interaction where we'd have 3 so here we have a bending motion between these 3 involving these 3 atoms and a stretch involving 2. And so that would be a G2 because there's 2 atoms in common, and it would be NR phi. Okay, so there are more symbols than this in the tables, but I think this is so beautiful. And it's even worse because then when you go to look up the elements, G11, G11, suppose we have the one internal coordinate is a stretch. Well, G11 is then equal to G2 R31 R31. In other words, it's 2 identical stretches, and then you're told to write mu1 plus mu2. And this is 1 over the mass of atom 1, and this is 1 over the mass of atom 2. One place where you make mistakes. Mu sounds like mass, but it's one reciprocal mass. It's easy to screw up. Anyway, I'm not going to write more of them. Another place where you screw up is often distances appear, and they appear with the symbol rho rather than r. And those are reciprocal distances. So there are 2 places where you could be led to think you understand, especially if you're using a table you didn't make. But once you have considered that, it's done. Okay, so you have this G matrix, which you need to describe the kinetic energy of the vibrating molecule. And once you have it in symbolic form, you can put in the masses and the distances and the angles, and you can make this a numerical matrix. And so you can derive the numerical G matrix. And for water, it's a 3×3 matrix. The elements have different units. And the elements not only have different units, I'm using forbidden units of dynes, millidynes. Most of you don't even know. I gave a lecture in France a few years ago, and I was nearly killed when I started talking about dynes and ergs rather than newtons and joules. But anyway, this is an old subject, and I learned it a long time ago. My notes have dynes. But the important thing is that you can convert the units to something more universal. And so anyway, you get the G matrix and the F matrix. Now, the F matrix is the matrix of force constants. what are the what force does it take to stretch to change the various internal coordinates? And one could get these elements of the force constant matrix by fitting a lot of spectra or by doing an ab initio calculation. But when you do an ab initio calculation, what you get is not a 3n minus 6 by 3n minus 6 dimensional force constant matrix. You get a 3n by 3n matrix, and you have to do a transformation to reduce it to this. Okay, but that's, if you have the S's, then you can do that. I'm just not going to talk about it. Now, in this case, for water, we have 3 normal mode frequencies. And it's a 3 by 3 matrix. And so in this 3 by 3 matrix, we have 6 linearly independent elements. And that's too many. Well, G and F are both symmetric matrices. And so how do you get all 6 elements of the force constant matrix? Well, you fit isotopic spectra, you do complicated stuff, but you can do that. You can eventually get 6 elements. It's not as trivial as you might think, because what you want is the harmonic force constant. And what you get in the spectrum is a difference in energy between V equals 0 and V equals 1. And if it's a if it's not a diatomic molecule, there's cross anharmonicities between all the modes, and somehow you have to back that all out. And it's not so trivial to do it, to get this from the spectrum. But in principle, you could imagine you could get that experimentally. Okay, so this is a symmetric matrix, and this is a symmetric matrix. What we want is this combination of G and F. And this is the matrix whose eigenvalues we want in order to determine the normal mode frequencies, and whose eigenvectors we want in order to determine the forms of the normal modes. So if we have these 2 matrices expressed in numerical form, it's trivial to multiply them. Symmetric matrix, not a symmetric matrix. That's a surprise. But you can prove that it's not symmetric just by taking 2 symmetric 2 by 2s and multiplying them. You discover you're not guaranteed. And when you have a not symmetric matrix, you cannot diagonalize that by a unitary transformation. You diagonalize it by a similarity transformation. The computer does it. You don't care how it does it. You just have to instruct it slightly differently. And you want to know what transformation it used to find the eigenvalues of this matrix, because you're going to use them. Okay, so for the water example, we have the numerical G and F matrices. We have GF, and so as soon as we have this, we can write the secular equation, and the roots of the secular equation are 3 numbers, also with 3 different units. Oh, that's not true. No, there are 3 numbers with the same units. And converting to useful units, they all have units of seconds to -2. And what we want, so we have 3 eigenvalues, lambda 1, lambda 2, lambda 3. And what we want is the square roots of these things, because those will be frequencies. But we're spectroscopists, and so we don't want frequencies. We want reciprocal centimeters, and so we divide by the speed of light. So we get 3 eigenvalues and the 3 eigenvectors that correspond to these eigenvalues. And they have the frequencies 39, 42 reciprocal centimeters, 38, 32, and 1648. Okay, so that's what comes out. And these are, in fact, the normal mode frequencies of water. But there's one thing that's wrong. They're numbered wrong. The computer solves this problem, and it numbers, or it gives you a list of eigenvalues in some order, and you might call them 1, 2, 3. It doesn't know anything about spectroscopic conventions because it's a computer. It's not an insane person. There is a spectroscopic convention for numbering the normal modes of any molecule. And I should talk about that for a moment. If you're a spectroscopist and you say, I have a molecule, say benzene, and I say, okay, nu 18 of benzene is something, you immediately can figure out what that, which symmetry species that normal mode has, and whether it's predominantly a bend or a stretch. Maybe not immediately, but there is no possibility for disagreement, because the international convention on how you number the modes is well established. What do? Well, we have two different things. We have frequency and symmetry. So it would be a child's play if we just took all the eigenvalues of this matrix and listed them in numerical order and say the largest one is mode 1 and the smallest one is mode 3n minus 6. And that would be a correct thing to do for a molecule that has no symmetry. But when there is symmetry, as there is in water, water has C2 symmetry, it has reflection planes and all that sort of good stuff. It belongs to what point group? C2V. Right. And C2V has symmetry species, 4 symmetry species. And so what you do is you first number the totally symmetric modes in order, and then you go to the next. There is a convention for which you do second. It's this one.
Is it just down the character table?
No.
The character table is going to be A1, A2, B1.
Yeah.
It might be, and then you would go down the character table, but it's A1, then A2, then B1, then B2. And if it were in C2H, it would be AG, then AU, BG, then BU. There's lots of, but once you see what the idea is, you can figure out how you assign modes to symmetry. Now, you don't know at the present time for an arbitrary molecule how many modes there are in each symmetry species. That is a fairly beautiful and standard problem, which I don't know. If I run out of things to talk about, I'll do it. But it's too easy. And there's also a simple group theoretical method for deciding whether a particular mode is predominantly stretch or bend or a mixture, and what kind of stretch or bends. So there's some very nice stuff that you can do just with group theory to describe the essential characteristics of all of the normal modes. And so if someone tells you the mode number without too much work, all the hard work has been done getting these frequencies. And if then that person knows the rules and says this is nu 18, then you can do the group theory and figure out what is the essential characteristic of that mode. And that's really very wonderful. Okay. So we diagonalize, we get the eigenvalues of the GF matrix, and we also get the L matrix. And the L matrix is a bunch of numbers. And in order to go from the simple things, the internal displacements, to the things we want, the normal displacements, we need the inverse L matrix. And there's two ways of getting that. One is you have a numerically defined matrix. You can tell the computer symbolically, because it knows linear algebra better than you do, how to find the inverse matrix. There is also another relationship that came as when we were dealing with the analysis of the vibrational problem. We saw that this had to be true. The L matrix multiplied by inverse of the G matrix multiplied by the conjugate transpose of the L matrix. And since these matrices are real, conjugate transpose is just transpose. We could get the inverse yeah, that's right. We could get the inverse L matrix simply by multiplying this on the left, on the right, by the inverse. So we have L dagger, G minus 1, L minus 1. So symbolically, the inverse L matrix is just L dagger, which you know, and G inverse, which you don't know. You have to invert G. So some matrix is going to have to be inverted, either L or G. Doesn't matter. Okay, so once you now have the eigenvectors, once you have this L matrix, this L inverse matrix, you can write what each of the normal modes is in terms of the internal displacements. And when you do that, you can begin to draw pictures of what the motions of the individual atoms in the molecule look like. And from those pictures, you can say what the name of the mode is: symmetric stretch, antisymmetric stretch, bend, simply by seeing how these vectors look. And so the L inverse matrix tells you how to build this out of the internal displacements. And then you just draw vectors in the appropriate directions and lengths. And you can see what the matrices look like. Now, on page 5 of the notes, Q1 and Q2, the indices are reversed. Because this is a combination of notes written years apart. And I discovered only after combining them that I used a different convention. Okay. So by looking at the eigenvectors, you can just say that Q1, the one with the frequency of 38, 32, is a symmetric stretch, because the two identical bonds are oscillating in phase, and they're oscillating by the same amount. And we can call this thing, the one with 39, 42, the anti-symmetric stretch. Now, I have a little bit of an anal compulsive streak in me that when you have two identical bonds, there are symmetric and antisymmetric stretches. For other cases, it's okay to talk about asymmetric stretches. But when there's two, and you can have them symmetric, you can have them with the same phase or opposite phase, it's symmetric and antisymmetric. And I'm sure that you'll all have a laugh about that. And then this other one, the low frequency guy, is the bend. And the vectors tell you all about that. Okay. Now, in describing the various normal modes, Q1 is written as minus 0.685 S1 plus 0.685 S2. Two internal stretches. And Q2 is written as 695 S1 plus 695 S2 plus 0.037 S3. Notice we have two equal numbers of opposite signs. Here we have two equal numbers of the same sign and a little bit of this bend. So these are two stretches, out of phase and in phase, and a stretch and a bend. And Q3 is just 655 S3. So the three normal modes have this form. Notice there's no S3 in Q1. There's S3 in these two. S3 is the bend, and somehow this guy doesn't have, now these numbers come out equal because the eigenvectors of a matrix said they're equal. We're not imposing any symmetry. These numbers came out equal and opposite. These numbers came out to be the same, again, because of the structure of the matrix. These two numbers are very different in magnitude. This guy is predominantly a bend. It has a little bit, I'm sorry. This guy is basically a pure bend. This is predominantly a symmetric stretch and has a little bit of bend in it. Why just a little bit? How do the G and F matrices tell us about the mixing of the internal coordinates? So you look at these and you see, oh yeah, it's obviously antisymmetric, symmetric, and this is obviously a bend, and this is a stretch with a little bit of bend in it. Okay, so what do we do?
What are the rules that you use for normalization?
There's no normalization.
Okay.
I mean, you started with normalized quantities somewhere over here.
The little ST alphas are normalized.
That's right. And so you're building, you start with normal, you start with unit vectors. And so everything then is normalized in that sense. So you're mixing these ST alphas, and all this is just several steps of transformations of the ST alphas. So these, there's no normalization at all. I've often thought about that. What do these numbers mean? Is there some, it's so close to, this is very close to 1 over the square root of 2, but it's not. And this is also very close to 1 over the square root. It's closer, but it's not. And and this one is just an orphan. And you would expect, in fact, I'm a little puzzled at whether there should have been some more stuff here or not. But anyway. So it is reasonable to ask, can we, by looking at the F and G, I'm getting ahead of myself. Can we, by looking at the F and G matrices, understand the specific, or at least the qualitative things that determine how much stretch, how much bend is mixed into a predominantly stretch? When you have normal modes of the same symmetry, they are going to be mixtures of the of combinations of internal coordinates of the same symmetry. But what is the detail of that mixing? Can you, by looking at the F matrix and the G matrix, say, yes, there ought to be a lot of mixing of bend with stretch, or no, there shouldn't be? What are the dynamical factors? But I got ahead of myself, and so I'm going to take a brief, yeah.
So if those, like Q3, that number seems like anomalously small.
Right.
Does that really tell you that the magnitude of the motion, if you have like 1 quantum of bend, that like the atoms don't move as much?
No, I think it's just that 3 atoms are moving.
Okay.
I think that yeah, S3 involves 3 atoms moving, whereas S1 and 2 have 2 atoms moving.
Okay.
If you decompose big S3 into little ST alphas that comprised it, then
That's right.
Then you could tell.
Yes. In fact, when you draw these famous pictures of arrows pointing of definite lengths and definite directions, those comes from the ST alphas, and so you know what they are, and that's what the normal modes are said to look like. And so those vectors aren't arbitrary objects, although frequently you draw them in a symmetry sense as opposed to a numerical sense, but that's always close. Okay, suppose we have two or more identical bond lengths, or two or more identical internal coordinates in a molecule. In water, there's two identical bond stretches. In other molecules, you might have more than two. In benzene, you have 6 identical CHs. But in toluene, it's not that you have 5 identical CHs of one flavor and 3 of another. You have 5, and they come in 2 ortho, 2 para, 2 meta, and 1 para. So, okay. So you can symmetrize. You can build linear combinations of identical internal coordinates. For example, so here is what's called a symmetrized internal coordinate. Now, people use different notations because they like to use S for symmetrized internal coordinates, but S has been taken. And so what do? Well, some people use S for symmetrized internal coordinates, and they pretend that it hasn't. So you have some matrix that combines the individual non-symmetrized internal coordinates. And so if, in the case of water, this matrix would have the form 1 over square root of 2, 1 over square root of 2, 0, 1 over square root of 2, minus 1 over square root of 2, 0, 0, 0, 1. I mean, it's really easy if there's only 2 objects. You just have a normalized thing, and that's easy. So we define the symmetrized coordinates by applying this transformation to the non-symmetrized things. The F matrix elements are given by this. So these are the non-symmetrized things. This is the, okay, and now we can insert 1. This is a unitary matrix as opposed to just a matrix. It's a normalization preserving matrix. We can rewrite this as U dagger U F U dagger U S. We've just inserted 1 into this formula twice. And I did it right. And so we can then rewrite this and say S twiddle, F twiddle, S twiddle. This transformation takes this to this. And so this is the symmetrized force constant matrix, and these are the symmetrized functions. In that representation, what we find is that the force constant matrix is block diagonalized. And it's block diagonalized in the representation I've been using. It's block diagonalized in the sense where we have 0 here, 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 and here, and numbers here and here, and that's awkward. And so you simply rearrange rows and columns, and you end up having the force constant matrix with numbers So it becomes a symmetric matrix. There's a 2 by 2 symmetric matrix and a 1 by 1. It has block diagonalized. So this transformation, where all you do is you say, I have two identical internal displacements. I don't know about group theory. It has transformed this 3 by 3 matrix into a 2 by 2 and a 1 by 1. And amazingly, it does the same thing to the G matrix. And so you can factor the F matrix and the G matrix both into 2 by 2s and 1 by 1s. And when you do that, the GF matrix is also of this form, where you have a 2 by 2 and a 1 by 1. And this block is associated with the totally symmetric levels, the bend and the symmetric stretch, and this block is associated with the antisymmetric level. Okay, so now we've discovered that even though you don't start out by using group theory, you can factor this problem into the simpler units. And that's wonderful.
And does G squiggly, F squiggly diagonalize to give you an L squiggly?
Yes, I believe so.
Okay.
Okay, so now, what actually, can one look at, I mean, when you have a Hamiltonian, you can look at the form of the matrix, and you can say there are off-diagonal elements that are, there are diagonal elements that are very different, and there's an off-diagonal element coupling those two diagonal things, which is small compared to the difference in the diagonal element. And when that happens, the off-diagonal element has a negligible effect on the problem. And so one is always interested in making a comparison of the off-diagonal element to the difference in diagonal element. So in this case, we have G13 twiddle, and we have G11 twiddle minus G33 twiddle. And we'd like to compare them. And we have F13 and F11 twiddle minus F33 twiddle. And so even though GF is not a symmetric matrix, we can use some of the same ideas we use for reading symmetric matrices. And so the off-diagonal elements, G13 and G31, yes?
Don't you care about the diagonal and off-diagonal elements of GF, not of G and F individually?
You do, but you can build it up. I mean, yes, you care about GF, but if there's big differences here or here, that will carry over into the big differences in GF. And
can they cancel out though also?
Yeah, there's lots of problems, but what you want is some qualitative rules for deciding by looking at masses or adjusting masses or designing a molecule to say, I want to minimize the mixing of two different kinds of internal coordinates. How do I do that? What causes that to happen? And there's kinetic energy coupling, which is expressed by examining the G matrix, and there's potential energy coupling, which is obtained by examining the F matrix. And so you can look at both, and you can draw conclusions. So on page 10 of my notes, I have a formula expressing G13 in terms of a bond length and an angle and a mass. And this is a fairly famous Brooks Pate and Kevin Lehman idea that if you want to minimize coupling between two halves of a molecule, if you put a heavy atom between them, it will shut that down. And so in this G13, there's a 1 over M3, which was the center atom. Heavy makes the G13, the coupling matrix element, small, and so that shuts down the kinetic energy coupling. Now, this difference would be, these numbers are small if the end atoms are heavy and are large if the end atoms are light. And so you can look at the structure of the G matrix and you can design a molecule either by isotopic substitution or replacing carbon with germanium. That's what they did. And you could try to minimize the communication between the different parts of the molecule. And the force constant matrix is similar. Okay, one of the things that you discover is force constants for stretch force constants, or stretching force constants, are much larger than bending force constants. And because of that, suppose in the case of water you have a symmetric stretch and a symmetric bend. They belong to the same symmetry species, but there's a huge difference between the force constant for the stretch and the bend. And as a result, you have built into the F matrix a big difference in diagonal elements that fights the small coupling between the stretch and the bend. And this is the physical basis for the distinction between bending modes and stretching modes. Occasionally you have an irreducible representation, a symmetry, where there's only a stretch or only a bend. For example, in formaldehyde, the A2 symmetry is unique for out-of-plane bend. And so that's a pure out-of-plane bend. There isn't any stretch. But there are often a stretch and a bend, or maybe two different classes of bends or two different classes of stretch. And as long as they belong to the same symmetry species, they'll mix. And you can make judgments about what causes the mixing based on masses and about these qualitative things. And because bending, it's easier to bend than to stretch, there's usually very little bend character in stretches. And you call things stretches and bends. What time is it? Have I talked too long? No. Okay, so I haven't gotten to page 11 and 12, and I'll probably begin my lecture. I mean, there's some virtue in this because I'm not going to have any time to prepare for tomorrow morning's lecture. So I'll start with something I really know for tomorrow morning. Okay, so that's it.